Welcome to MEI Mechanics. We're on the topic Mechanics Basic Principles, and this is video 1.3, Forces. So what is force? Well, it's a vector quantity, so it has both a size and a direction, and the SI units are newtons, and typically you'll have several forces acting on a particle at the same time. And so it's the size and direction of all those individual forces which will then combine to give the overall force which is acting on the particle. Now, it may be the case that that particle remains at rest or continues to move at a constant velocity, and those things will happen if the forces are in equilibrium. So those forces balance, so there's no overall force acting on the object. We'll say a little bit more about this idea in the next video on Newton's laws. The other thing that could happen is that the particle might change its speed, or it might change its direction, or both, and those things can happen if the forces are not in equilibrium. Now, in physics more generally, there's lots of types of forces out there. In A-level mechanics, we're going to look at a small number of forces, and we'll say a little bit more later in the video about what some of those forces are. Now, it's important in mechanics to make the distinction between mass and weight, because often we think of these things as being the same thing, but they're not. So if you see a set of scales like this, you place a 1 kilogram mass on them, and they give you a reading of 1 kilogram. What that is actually showing is not the weight of the object, it's actually showing you the mass of the object. Alright, so if you were to put those scales on another planet, different size from the Earth, they'd give a different reading. And that's because this thing would have a different weight. However, because we're assuming these scales are based on the Earth, they are calibrated to read off in kilograms. So let's make clear the distinction then between mass and weight. So mass, that's the property of the object that doesn't depend on where it is in the universe. So that 1 kilogram mass, that will have a mass of 1 kilogram no matter where it is. If we're on the surface of the Earth, then there's a certain amount of gravity at the Earth's surface, and we use the symbol G to represent the strength of the gravity on the surface of the Earth. Alright, and it turns out the units of that are the same as the units of acceleration, because actually irrespective of the mass, all free-falling objects will accelerate at the same rate. And so we call this often the acceleration due to gravity. And that's 9.8 meters per second squared on the surface of planet Earth. When you combine those two things together, the mass and the gravity, that's when we get the weight. Alright, and that's the force which acts on an object as a result of the gravity which is acting on it. And that's the product of the mass and little g. That gives you the weight. So for 1 kilogram mass on the surface of the Earth, its weight is 9.8 newtons. So when we've got those kitchen scales, they are measuring the weight, or at least they're detecting the weight, but they're giving you a readout of mass. Because it's assumed that they are going to be on the surface of the Earth, and the thing that you probably want to know about the object is its mass. So what types of forces are there? Well, most of the diagrams we're going to be doing will be drawn for just a few different types of force. These diagrams must be clear, and the forces that we should be including are things like this: weight, air resistance. That occurs when something's moving, usually at high speed, either through the air or possibly through a different type of fluid. Tension, so that's where we've got more than one object, possibly connected by a string or a bar, and there are forces between the two objects mediated via that string. Driving force, now that usually occurs when we've got a vehicle moving, and we think of the force which is ultimately coming from the engine of that vehicle, which is pushing the object forward. But also someone, just a person walking, they are also experience a driving force which is generated from within their own body, which is what's moving them forward. Then we have the normal reaction force, so that's any time where an object is in contact with a surface, and that always acts perpendicular to the surface. and that sort of partners up with the frictional force, which again is between surfaces, but that is parallel to the surface. And so those two things together, the combination of normal reaction force and friction, is the overall reaction force from a surface. And if there are any other forces mentioned in the question, they would just go into this other category of all other forces. So let's have a look at the idea of force diagram. Now in a force diagram, what we're trying to do is simplify the situation as much as we can. Okay, so we'll think of the object as a particle, represented by those black dots at the bottom, and then we'll represent the forces using arrows. So we've got a book there at rest on the table. What forces are acting? Well, clearly the book has a mass, and that therefore generates a weight, and that weight acts downwards. So we can always draw an arrow representing the weight on any object which has mass. Now, if that was the only force acting, then we'd expect that object to start to accelerate downwards. Now, usually if a book's resting on the table, that doesn't happen. So there must be another force acting so that overall we have equilibrium. And as we'll talk in more detail about in the next video, that will have to be equal and opposite to the weight in order to balance it and to have no overall force. And because that is acting perpendicular to that surface, that's a normal reaction force, and we've given that the symbol R. Now let's turn our attention to this swimmer. There are more things going on here, because that swimmer, as well as having a weight, is also applying a driving force to propel himself through the water. So we usually give that the symbol D, and if we assume this swimmer is travelling at a constant speed, then there must be an equal and opposite force acting so that we have overall equilibrium, and that is the resistance force from the water. Very similar idea to air resistance. We mentioned that the swimmer has a weight, and then there must be a force, again we'll call this R. It's maybe a little bit different from usual normal reaction force. It's really the buoyancy of the swimmer, but that's acting perpendicular to the surface of the water, so it's behaving like a normal reaction force. So we have four forces acting there, which, if the swimmer is moving at constant speed, will be in equilibrium. A couple more examples. A car on a motorway, very common example to see in mechanics problems. That has a driving force. It will experience air resistance and other frictional forces as well, which will oppose its motion, because those resistances always oppose the motion. It will have a weight, of course, and a normal reaction force from the road. So, in the end, very similar situation to the swimmer. And finally, we're going to talk about the skier. Now, this skier is on a slope which is not horizontal, and that is going to complicate things slightly, so we need to think carefully about what's going on. There will be friction between the skis and the snow, and that will oppose the motion of the skier. So there must be friction acting, and that has to act parallel to the surface. So there's the friction. The skier has weight, and the thing to remember about weight is it always acts downwards, so it doesn't matter what direction the slope is, the weight is always straight down. Now if we look at those two forces together, they clearly can't be in equilibrium because they're not opposing each other completely. So if the skier is going to continue at a constant speed down this slope, there must be another force acting, and that of course is the normal reaction force, and that is perpendicular to the surface, like that. So R and F, the normal reaction force and the friction, are always going to be perpendicular to each other, but in this case they're not parallel or perpendicular to the weight because of that slope that they're on. A little bit more about force diagrams. Well, here's a situation that you'll see from time to time. This is where we've got a mass which is attached to two strings. Now the thing about strings is that they'll just bend whichever way they're pulled in. So the tension in the string will always act in the direction of the string. It's the only way the string can support tension. And if the strings are not attached to each other, so they're independently joined to the mass, then there's no reason why those tensions have to be the same as each other. So we've got T1 and T2 here to indicate that these could be different size and direction of force. And of course the weight, which is mg, is acting downwards. However, if the situation is more like this, just look very closely at not just the diagram but also the worded description here, that these strings are threaded together. So imagine there's a little hoop there, and this is really just one piece of string which threads through. Then, assuming there's no friction between the string and the hoop that it's attached to, that means that the tension then has to be the same size either side. It can still be in different directions, but you'll have the same size of tension in each. So we'll use the same symbol then. That T will be the same value. And again, there's a mass acting, a weight acting downwards. Okay, here's a more involved situation. Lots of things to think about here. So we're going to very carefully try to draw each of the forces which is going to be acting here. Well, let's read what it says first. It says the car has a mass of 900 kilograms. So the first thing that we can do is on the car we can show a downward facing arrow, 900 kilograms, so that's the mass of 900 multiplied by the strength of the gravity, which is g. So that force of 900g will be acting downwards on the car. It's towing a caravan, and the caravan has a mass of 700 kilograms. So we can draw that there on the caravan. That's 700 times g is the caravan's weight. And then it says it suddenly brakes and decelerates at a constant 1.5 meters per second squared. So to indicate this is not a force, so I'm not going to draw it on the objects themselves. And the standard way to indicate an acceleration is to use a double arrow like that. So just to be clear, that's the acceleration of, well, both the car and the caravan. They're attached to each other, so they'll be doing the same thing at the same time. And that's 1.5 meters per second squared. Air resistances, so 100 newtons and 300 newtons respectively. So the car is 100 newtons. Now air resistance always acts to oppose the motion. Now even though the car is accelerating to the left because it's braking, it's travelling to the right. So if the resistance is opposing the car's motion, then the resistance must be acting to the left. And that's 100 newtons on the car, 300 newtons on the caravan. Now, the only things that we haven't taken account of yet is the fact that the car and the caravan are attached to each other. Alright, and they're attached via this tow bar. Now, certainly in the normal situation of a car towing the caravan, this bar is going to be under tension. So what that means is it's going to be pulling it on the things it's attached to. So on the car, there'll be a force on the car acting into the tow bar, T. And just like we were mentioning about the string, the tension must be the same at either end. So that means that there's the same force acting on the caravan, but in the other direction, T. Now, one thing to say, that if you ever encounter a problem like this, is that with a tow bar, it's possible, depending on how hard the car is braking, it is possible that when the car is braking, that tow bar could actually end up going into compression. That's not a problem mathematically, okay? All it would mean is that this T would then have a negative value. So we could either keep it as a negative value with the directions acting as they are there on our diagram, or we could switch the directions and keep a positive value. Mathematically it amounts to the same thing. Alright. Now, there is just one more force that we haven't thought about yet, and that is because we're told that the car is now braking. Um, how what effect does braking have in terms of applying a force to the car? Well, when a car brakes, it's trying to slow its wheels down, and so the wheels are going to be interacting with the road in order to generate a force which is going to be opposing the motion of the car. Now, any force like that, any force which is perpendicular to the road and is mediated between the wheels and the surface, must actually be friction. Um, so there is a force, a frictional force from the wheels acting on the car. We're not told what that is, but we must at least acknowledge the fact that there's a force there acting from the wheels on the car. Okay, so there is just the same diagram again, just a bit neater. Alright. Um, just one thing to say about deceleration. Again, we could have this arrow, which is representing the acceleration, pointing forward still with a negative value. A bit like what we were saying about the tension. There's always that choice. Personally, I think if you know what direction something's going to be acting in, then it makes more sense to have the arrow going in that way. But often in the question, you don't know until you've worked out the value whether it's going to be positive or negative. So you need to be able to interpret the negative value correctly. Alright, here's another example then. This time I've got a pulley. Now the thing that you need to know about pulleys is that we're always going to model them as being frictionless. And what that means is, in practice, is that the tension in that string is going to be the same all the way along the string. Alright, so whatever tension you have acting on the 3 kilogram mass is going to be the same tension acting on the 7 kilogram mass. Now, obviously the 3 kilogram mass will have a weight of 3g, and there'll be this tension T acting on it from the string. As we said, that same tension, same value must be acting on the 7 kilogram weight, and then we've got its weight acting downwards. Now for this video, this is as far as we're going to go, but clearly this system can't be in equilibrium. Alright, even if one of those seemed to be in equilibrium, the other one wouldn't be. Okay, so we know that something would happen in that situation. And just sort of common sense would tell you that because you've got a heavier weight on the right, that one's going to move down while the other one moves up. But it's important, because this string is inextensible, that means it can't stretch or squash. The acceleration of the 3 kilogram mass upwards must be the same as the acceleration of the 7 kilogram mass downwards. If one moves up, the other must move down by the same amount. So that concludes video 1.3, forces. The next video will be video 1.4, Newton's laws.